All right, good afternoon, and we'll try to start on time so that we can stay on time. And despite the fact that we have only 3 talks, we have to stay on the other schedule so that people who are changing rooms can do that. So we have 3 interesting speakers representing at least 2 generations of folks here in the department. And our first speaker is Mark Harris, now works for NVIDIA. And in the tradition of the department, I'm going to tell you some things you may not know about him. He helped design the logo on the shirts that we wore at SIGGRAPH 2002.
And Greg posed for it.
Greg posed for it. I was going to get to say that.
Oh, sorry.
I introduced him.
Oh, yeah.
What you're seeing is a time lapse of the setup and execution and teardown of our demo that summer. Another thing about Mark is he lives in Australia, and he lives on a compound of commune.
It's not a compound. I'm not a doomsday prepper.
Of his wife's family, and they are personally building the guest house while their next main house is being built. So, with that said, Mark, welcome.
Thanks, Mary. It's nice to be back in 2011. It's like, coming home. So, let's see. Yay, okay, cool. So, yeah, as Mary said, I work for NVIDIA, and I do work in Australia. I work from home. I work remotely, very remotely. What I did for my PhD, I still work on today, and that's general purpose computing on GPUs. And so I thought I'd give you a little bit of a flavor of the history. Of course, with only 20 minutes, I can't do everyone in that history justice, so I apologize for omissions, but it is heavily biased towards NVIDIA and UNC. But a lot of stuff happened in the history of GPUs at UNC. So yeah, so as Mary was saying, this is where I live. This is our view where we're building our house. This is the house that we're building. That's a photograph. This is a rendering. My father-in-law designed the house. Most of it, we've modified it and started building it almost 25 years ago before he passed away. So we're finishing the work that he started. And so, yeah, it's going to be a very beautiful place to live. That's where it is. It's called Larnook, New South Wales, about 3 hours from Brisbane, where we lived until about a year ago. So yeah, GPGPU, what I'm supposed to be talking about rather than what I'd like to talk about. GPGPU is about using graphics processors for something that they weren't originally designed for, which is general purpose computation rather than a special purpose computation of graphics. Of course, as you'll see, some of the early GPGPU really was done on general purpose processors. That just happen to be graphics processors also. And that's sort of where it's come to full circle. GPUs have evolved to be general purpose parallel processors quite deliberately. And it's no longer kind of contorting something that for purposes it wasn't intended for. But so let's start at the beginning. Nick England and Mary Whitten founded Iconis Graphics Systems here in North Carolina, I think 1978, and created the RDS 3000. Is Nick here? Oh yeah, good. Okay, cool. And I was happy to see that you recently added videos to the website, which if it weren't for Google, nobody would be able to find it because it's on the Virginia International Raceway history page. So I was happy to find, because I'd seen this page before, but in preparing this talk, I wanted a little bit more background and maybe some pictures, which I found, which is good. And in one of the videos, which shows this code that I think Tim Van Hook wrote for CNC milling operations, Nick actually says, he says, all computation is taking place in the Adage 3000 display. So this Adage, or the Iconis RDS 3000 was, if I'm not wrong, basically a frame buffer and a 32-bit processor for graphics data generation. And so Tim Van Hook used that for not just, transforming triangles, but actually generating the data using solid modeling and for ray tracing. And this is a ray trace image shown here. So that was very early. I was 3, so. But that really was probably the first GPU.
Wait. You're joking, right? You weren't 3 years old, were you?
Yeah, I was 3 years old in 1978, yeah. This event is about feeling old. No, it's just everybody I talk to is like, oh my God, it's been 15 years. Wow. So yeah, UNC has a long heritage of really cool work on custom computer architecture designs for computer graphics. I'm not familiar with recent history in this area. I hope that this is still going on. But when we were here, it was kind of just the very end of this I started. The pixel flow was still plugged in, but the pixel planes machines and pixel flow are basically these massively parallel graphics computers, and they were used for non-graphics computations a little bit, often with a graphics end result. But for example, Rhodes et al. Published a paper on using Pixel Planes 5 for procedural texture generation, and they used those for generating the textures in the Brook's house walkthrough, I think. So that's what's shown here. So generating like the wood textures or the tiling and things like that. And then PixelFlow, which had over 100,000 little not so powerful processors, but many of them, which is very similar to GPUs today in a lot of ways. Enabled some of the earliest real-time programmable shading, which Mark Alano and Selmo did. And then Kedem et al. From Duke, I think they must have got some time on PixelFlow, and they implemented Unix password cracking, so brute force password cracking on PixelFlow. And that's interesting because, fast forward to today, and people are doing cryptocurrencies, and so rather than using GPUs to steal money, they're using it to print money. But but actually, GPU Bitcoin mining is kind of a fad that passed in 2013 because now it's more efficient to use custom ASICs for that. So, okay, so I'm going to run out of time if I keep going at this pace. GeForce 1 to 3 were kind of the dawn of GPUs. So in 1999, NVIDIA released the GeForce 256, which they coined the term GPU for. Basically, they said, oh, it's not Intel, just Intel, you can sell PUs. So they created a GPU, and they actually made a specific definition for what that is, and it's something like a card that can do hardware transform and lighting and achieve at least 10 million triangles per second or something like that. But it had some early programmable features, something called register combiners, which continued for the next couple generations. And then in GeForce 3, they introduced the first programmable hardware that you could actually program with an assembly language, which was the vertex shaders, as well as data-dependent texturing, which is probably more important for this early GPU, where you could look up from one texture and use that as an offset to look up into another texture. And so that enabled some of the early GPU stuff that happened on gaming hardware. Kenny Hoff was using TNT2 rasterization, and as well as the SGI reality engine to do Voronoi diagrams. And so that was one of the kind of eye-openers for me, because we were concurrent, and seeing stuff like that kind of got me thinking. You kind of turn how you look at this special purpose hardware, and you can think about other ways to use it. Scott Larson, Dave McAllister did the first GPU matrix multiplication on GeForce 3 also. And then in 2001, my personal connection to this was that I went to NVIDIA for a summer, and there are these SDK demos that were written by Greg James of the Game of Life and this shallow water simulation, which just looks like a blue square there. He'd written these cool multipass shading implementations of these, physics simulation and cellular automata simulation. And so one of my tasks was to port those to OpenGL from Direct3D. And so I learned how to do that. And I was planning to do a PhD, which I did. I was planning to do a PhD on cloud rendering. This was rendering clouds, not rendering cloud. I didn't invent the cloud. What I wanted to do was the simulation of clouds, and I wanted to do that in real time. And so I kind of got the idea from this that pretty soon I would be able to do the simulation and the rendering on the graphics hardware. So came back to UNC and worked with Greg and Torsten and Selmo to do this work on physically based simulation on GPUs. And this was very simplified. It was basically cellular automata, but with continuous state, something called a coupled map lattice. And we did boiling and convection and chemical reaction diffusion. And they were all pretty rubbish simulations because of the precision. So you only had about 10 bits of fixed point precision in the pixel shaders. But it kind of showed what was possible. And we presented this in graphics hardware that summer, and there were lots of other people, not lots of other people, but there's several other people that I met who were doing similar things. And so that's when I kind of realized, oh, this is a thing, this using GPUs for, well, there's a few, people were calling it all different names, all mouthfuls, like application of graphics hardware to non-graphics applications, or exploiting special purpose hardware for alternative purposes and things like that. And so I thought, well, we should call this something. And so I just kind of half-jokingly thought of GPU, because of the way it sounds, which is general purpose computing on GPUs, and created a homepage for that on my website, on my UNC website. And then Anselmo, about a year later, suggested, hey, we should probably get a domain name for that. And he registered, actually. And so that's still around. You can still go to gpgpu.org, and I still post news. If you have news, send it to me. I'll post it. But I'm not as actively pushing stuff on there anymore. But that year, 2003, floating point hardware became available. So we could finally do these simulations with the precision that we needed, or at least single precision, for visual simulation of fluids and things like that. And so this kind of enabled a lot more research. So there were a lot more people started doing GPGPU research. So gpgpu.org became kind of an active community, and it allowed me to finish my dissertation. So I did the cloud simulation, and this is a 2D capture. I did 3D also, but it wasn't nearly as fast, so it didn't make it as interesting, faster than real-time videos. But yeah, so that's that. So that was the GPGPU at UNC up to about 2003. So then I went and then got a full-time job at NVIDIA. And what I was surprised by was that I got there and I kept hearing people say GPGPU. I thought that this was just something that was, a few people were working on, and maybe it would fizzle. Maybe, I didn't know what the future was for it. But obviously people at NVIDIA saw potential, and people were using this silly acronym that I made up, which was cool. I was working on games initially, supporting game developers in Europe. And but when I had an opportunity, I would work on GPU stuff and encourage that. So, but then a little bit later, I learned about this secret project. Well, not even the next architecture, it was a couple architectures out, was going to be called NV50, codename, got changed to G80. And it was being designed with a dedicated compute mode. So no longer just pixel shaders, vertex shaders, but a mode where you're running threads, lots of parallel threads. And more importantly, those threads have access to a general byte addressable memory. So no longer is the pixel's location fixed in memory. You now just have a thread that can read and write memory as it sees fit, which combined with work on software, which became CUDA, which was created by Ian Buck, who's now my boss at NVIDIA, provided basically the first C++ language and compiler for GPUs. So CUDA C++ defines a minimal set of extensions to C++ to enable you to specify or express parallelism in your code. So you can call functions and tell the GPU how many threads are going to run that function, for example, and then each thread gets an ID that it can use to compute memory addresses. In a nutshell. So that the next year, 2007, when CUDA 1.0 came out, really began sort of a massive surge in general purpose GPU development. Interestingly, marketing decided at some point that we weren't going to use this term GPU because it harkened back to the old days of OpenGL-based GPU, which is hard because CUDA was supposed to, and really did, make GPU accessible to non-graphics PhDs. You know, it made it accessible to scientists and engineers. And in fact, a lot of the people who we fund these days aren't in computer science at all. You know, they're scientists or computational scientists. But eventually, when marketing realized that people were using GPU anyway, it became, you know, it was okay to say it. But we did start saying GPU computing instead, which is arguably a better name. So I do use that mostly. So fast forward to today, this is the kind of thing that GPU computing is enabling today. This is work from University of Illinois, using a cluster with 3,000 Tesla GPUs. Tesla is our line of high-performance computing GPU boards. The scientists at the University of Illinois did the first all-atom simulation of the HIV virus and discovered the chemical structure of its capsid, which is why they got a cover of Nature. And you know, that's the target for fighting the infection. So this kind of work, without the GPUs, the supercomputer would have had to be 5 times larger to achieve similar performance, or at least they would have had to use 5 times more nodes on a supercomputer, for example. And so this GPU computing enables faster discovery for science, or work on problems that potentially would have been too big without the GPUs. 5 minutes, okay. And so we've been reasonably successful with GPU computing at NVIDIA. There's a number of fields in which we have deployed lots of GPUs, and there's software written for GPUs. Oil and gas is a big one. Computations in higher ed. This tends to be a lot of things like the molecular dynamics simulation that was on the previous slide. Government labs and supercomputing centers. There's, I think, about 54 petaflops of Tesla-powered GPU supercomputing throughput in the world today. Several of the top 10 machines on the top 500 list. Computational finance, and then increasingly and more recently, consumer web applications, so enterprise data centers. So a little bit about that. This is the new hotness, which is machine learning using deep neural networks. I'm not an expert on machine learning, but it seems like it's everywhere at NVIDIA now. It's a really good application for GPUs. I'll just put it that way. But so if you have a neural network where you have all these neurons that are connected between layers, and it works by training it with large data sets. So you're passing through images, for example, if you're doing face recognition, and you design an architecture of these layers that has, for example, convolutional layers that do small filters of varying sizes on the input from the previous layer. And by training those with many, many images, they tend to almost kind of create the kind of edge detectors, for example, that you might manually have created without neural networks. And then feature detectors at deeper levels. And then at the end, you have these fully connected layers which kind of mix together those features so that it can recognize potentially many different faces or other things, or understand natural language, or tag images, et cetera. An example of this is the very large-scale image recognition challenge, which is held every year. And for years, the progress on this challenge was fairly constant in single digits every year. They were using traditional computer vision techniques mostly, a lot of manually tuned networks. And then in 2012, a group from Toronto used was the only group that used a GPU to train a new architecture of a neural network, and they got like 10% better than the previous year or something like that. And since then, well, now everybody's using GPUs pretty much for this kind of, for that challenge, but also for a number of different applications in startups as well as in basically all the major players on the web. So that's a good use for GPUs. I'm about out of time. I want to talk a little bit about what I do today, which is more working on our strategy and direction for GPU computing software. So working with our engineering leadership in the software organization to make sure we're aligned on what we're going to build for the future. So one of the things that we're really trying to do is dramatically lower the effort to program GPUs. Even though it's way easier than it was when we were in grad school, it's still hard to program heterogeneous computers. When you have multiple programmer types, parallel programming is hard in general. Then you've got multiple processors plugged together. So one of the things we're doing is unified memory. So here we have a heterogeneous system. You have a CPU, you have a GPU, they each have their own memory, and before unified memory, the programmer has to program to that explicitly. They have to manage memory in both places. They have to explicitly manage transferring data between them, have to be careful to overlap computation and data transfers to get the highest performance, et cetera. With unified memory, we basically give you a virtual address space that spans all the memory in your system, and the software today and the hardware tomorrow manages automatic migration of the data to the processor that needs to access it. So, so that helps a lot in porting applications to GPUs. Another thing we're working on is providing parallelism in mainstream languages. So, if you want to enable more people to write parallel software, you need to make sure that it's in the tools that they want to use. So, and if you, am I out of time yet?
Close.
Okay. Yeah. So if we we're working to enable mainstream languages to have parallel features, and we have various projects either at NVIDIA or with partners in all the ones on this slide as well as others. But one example is our involvement in the ISO C++ committee to introduce a parallel algorithms library, which is designed to basically give you the algorithms of this STL. If you're familiar with the standard template library, it has things in the algorithms library like for each or reduce, things like that. But providing this idea of an execution policy, which allows you to say, oh, well, this function that I'm applying to each element in the array is independent, so do it in parallel. Or you might have a vendor-specific execution policy that says do it in parallel on the GPU, something like that. So this is going very well in the standard, and we expect this to be part of C++ 17, which is the next C++ standard. So that's basically it. I just wanted to put up a few of the things I've learned from people from Fred Brooks and our CEO I have on here, but. Fred Brooks quotes, these both applied, I think, to writing PhDs or doing dissertations, but I think they're very applicable in everyday life, in your work. So the first one, I'm just saying, stand up. I wish somebody had told me when I was a new computer scientist not to sit down all the time when I'm working. I'm pretty healthy, and I'm still young, but I've had my share of sitting-caused pain. So stand up, teach students good health in their work. I think that's important. And then, these other things. Jensen, our CEO, says if you measure it, you can improve it, but you have to measure the right thing. So, okay. Thank you.
We can have a few questions for Mark.
So for the new STL standard, which I really like, is it can run on whatever hardware is available seamlessly. I don't
Automatically.
Everywhere. But optimizing which hardware it should run on in a heterogeneous environment sounds like a tricky problem.
Oh yeah. Well, I mean, it is a tricky problem. So,
We're going to disconnect you.
yeah. it is a tricky problem, and there's still probably research in that. But a start is to give you the tools to at least say, well, I know this is parallel, because the programmer knows better. But there is research on, automatically offloading or just-in-time compiling and things like that. Some of it in NVIDIA, some other research. But even that, for our C++ vision, that STL part is only half of the vision, or a third of it maybe. That's the high-level part. You still need to enable the ninjas to go down and do the CUDA kind of coding. And we would like that to be possible in the programming language or in the standard library also. But that's going to have to wait for probably another standard future beyond 2017. So that doesn't answer your question, I know.
Lots of questions. Thank you.
Any others?
We can take a couple more while Ming comes up and gets himself set. And since we have only 3 talks instead of 4, I'm hoping that the speakers will hang out when we get done and
Sure.
be available for individual conversations. Oh, how about one more pithy question for Mark?
Yeah, come on. No one? All right.
All right, let's thank him again. Thank you.
Computing on GPUs, and so I thought I'd give you a little bit of a flavor of the history. Of course, with only 20 minutes, I can't do everyone in that history justice, so I apologize for omissions, but it is heavily biased towards NVIDIA and UNC. But a lot of stuff happened in the history of GPUs at UNC. So yeah, so as Mary was saying, this is where I live. This is our view where we're building our house. This is the house that we're building. That's a photograph. This is a rendering. My father-in-law designed the house. Most of it, we've modified it and started building it almost 25 years ago before he passed away. So we're finishing the work that he started. And so, yeah, it's going to be a very beautiful place to live. That's where it is. It's called Larnook, New South Wales, about 3 hours from Brisbane, where we lived until about a year ago. So yeah, GPU, what I'm supposed to be talking about rather than what I'd like to talk about. GPGPU is about using graphics processors for something that they weren't originally designed for, which is general purpose computation rather than a special purpose computation of graphics. Of course, as you'll see, some of the early GPGPU really was done on general purpose processors that just happen to be graphics processors also. And that's sort of where it's come to full circle. GPUs have evolved to be general purpose parallel processors quite deliberately. And it's no longer kind of contorting something that for purposes it wasn't intended for. But so.
All right, good afternoon, and we'll try to start on time so that we can stay on time. And despite the fact that we have only 3 talks, we have to stay on the other schedule so that people who are changing rooms can do that. So we have 3 interesting speakers representing at least 2 generations of folks here in the department. And our first speaker is Mark Harris, now works for NVIDIA. And in the tradition of the department, I'm going to tell you some things you may not know about him. He helped design the logo on the shirts that we wore at SIGGRAPH 2002.
And Greg posed for it.
Greg posed for it. I was going to get to say that when I introduced him.
Oh, yeah.
What you're seeing is a time lapse of the setup and execution and teardown of our demo that summer. Another thing about Mark is he lives in Australia, and he lives on a
Let's start at the beginning. Nick England and Mary Whitten founded Iconis Graphics Systems here in North Carolina, I think 1978, and created the RDS 3000. Is Nick here? Oh yeah, good. Okay, cool. And I was happy to see that you recently added videos to the website, which if it weren't for Google, nobody would be able to find it because it's on the Virginia International Raceway history page. So I was happy to find, because I'd seen this page before, but in preparing this talk, I wanted a little bit more background and maybe some pictures, which I found, which is good. And in one of the videos, which shows this code that I think Tim Van Hook wrote for CNC milling operations, Nick actually says, he says, all computation is taking place in the Adage 3000 display.
Pound of commune.
It's not a compound.
Of his
I'm not a doomsday prepper.
of his wife's family, and they are personally building the guest house while their next main house is being built. So, with that said, Mark, welcome.
Thanks, Mary. It's nice to be back in 2011. It's like, you know, coming home. So, let's see. Second one. Yay, okay, cool. So, yeah, as Mary said, I work for NVIDIA, and I do work in Australia. I work from home. I work remotely, very remotely. What I did for my PhD, I still work on today, and that's general purpose